This is the very first telescope ever created. Galileo Galilei used a device like this back in 1609 to find the 4 biggest moons of Jupiter, and in doing so, he showed for the very first time that Earth was not the center of the universe. And this is the James Webb Space Telescope. It was sent into orbit in 2021, and its mission is to explore far-off galaxies, investigate the Big Bang, and uncover the true beginnings of the cosmos. The 4 centuries that stand between these two inventions have been filled with one driving force: our endless desire to understand what lies beyond the stars. The exact beginnings of the telescope are a little unclear, but we know the story starts in the Netherlands during the early 1600s. A spectacle maker named Hans Lippershey was playing around with the idea of placing different types of lenses on top of one another to make things look larger. His creation was remarkably simple. It was just 2 glass lenses fitted inside a wooden tube. The lens at the front of the tube is convex, which means it bulges outward. Light rays enter this lens moving in straight parallel lines. The curved surface of the lens then bends these light rays inward, making them all meet at a single spot. This process is known as refraction. If you've ever used a magnifying glass to focus sunlight into a tiny, hot point to start a fire, you've seen the same principle that the front lens of a telescope uses. The real cleverness of this design appears when you add the second lens at the back of the tube. This part is called the eyepiece. The eyepiece lens is concave, curving inward. For the telescope to work, you must place the eyepiece right at the location where the light from the first lens converges to a point. When the light hits this second lens, its inward curve straightens the light rays back out. So the first lens gathers the light and compresses it. Then the second lens takes that light and spreads it out, projecting a much larger image directly into your eye. That is the basic way a telescope functions. Those early Dutch models could magnify objects about 3 times. This was helpful for spotting ships on the horizon, but it wasn't powerful enough to peer into the depths of space. This is where Galileo enters the story. He was a brilliant thinker living in Italy from 1564 to 1642, and he is often called the father of modern science. His most important work, however, was in astronomy. This is also the work that got him into serious trouble with the Catholic Church, ultimately leading to him spending his final years under house arrest. In 1609, Galileo began to hear rumors about what the Dutch were doing with their magnifying tubes. Without ever seeing an original, he managed to build his own version in just a few days. But Galileo's telescope was far more powerful, achieving 20 times magnification. While people like Hans were experimenting with common eyeglass lenses, Galileo had the resources to select larger, higher quality pieces of glass. He then carefully ground these lenses to very precise curves. When Galileo first aimed his new instrument at the night sky, he began making astonishing discoveries. Looking at the moon, Galileo was amazed. He could clearly see that its surface was covered in mountains and craters. This immediately challenged the established view of the universe, which had been defined by the philosopher Aristotle in the 3rd century BC. Aristotle claimed that the sun and moon were perfect spheres made of a heavenly substance he called ether. But now Galileo was seeing the lunar surface with his own eyes, and it was clearly just a massive rock, rough and uneven, with mountains and valleys much like the surface of the Earth. This was a staggering revelation. But then Galileo looked even further. He pointed his telescope toward Jupiter. Even though he didn't have enough power to see the planet in detail, he noticed 4 small points of light near it. Over several days and weeks of observation, he realized these points were actually moons orbiting Jupiter, just as our moon orbits Earth. This discovery was even more radical. Aristotle had already decided that Earth was the center of the universe, and that all other celestial bodies moved around it. Since this was the accepted theory around the time of Jesus Christ, it was written into the Bible and became a core religious belief. But Galileo reasoned that if these smaller bodies were circling Jupiter, then it must be a common rule in the cosmos that smaller objects orbit larger ones. This would mean the moon orbits Earth, but it also must mean that Earth itself orbits the sun. This led Galileo to propose his own new theory, that the sun was the center of the universe and everything revolved around it. He wasn't completely correct, but he was much closer to the truth than anyone before him. The Catholic Church was not pleased, as this contradicted the Bible. This conflict eventually led to Galileo being tried by the Roman Inquisition, which was like the Supreme Court of its day. As a result, he spent the last 10 years of his life confined to his home. He could still write and invent, but his freedom was gone. After witnessing what happened to Galileo, other astronomers were hesitant to support the sun-centered model. It wasn't until Sir Isaac Newton introduced his theory of gravity in the 1680s that the true structure of the solar system was widely accepted by scientists. Speaking of Isaac Newton, he also had ideas for improving the telescope. He proposed using mirrors instead of glass lenses. This idea gave birth to the reflecting telescope. Again, we start with a tube, but this one is open at the front. At the bottom of the tube, a mirror is placed. This mirror is curved slightly, like a shallow bowl. The curve allows the mirror to act like the convex lens, focusing all the incoming light to a single point. At that focal point, a second, smaller mirror is positioned. This secondary mirror is flat and is usually set at an angle. It bounces the focused light to the side of the tube where the eyepiece is located. Just like in the earlier design, the eyepiece uses a concave glass element to take the concentrated light and expand it into a large image for the viewer. The main advantages of a reflecting telescope are lower cost and easier construction. Creating a very large clear glass lens is extremely difficult and, if achieved, would be incredibly heavy, making it impractical. In contrast, making a curved mirror is far simpler, and the final product is much lighter. The reflecting telescope made astronomy more accessible and allowed for the construction of much wider instruments. A wider mirror collects more light, making it possible to see objects invisible to the naked eye, like distant stars and galaxies. Throughout the 1700s and 1800s, engineers continued to refine both refracting and reflecting telescopes. While reflecting telescopes are more practical to build, they can have some issues with image quality. This is mostly because the secondary mirror sits in the middle of the light path, which can disrupt the light and reduce the clarity of the final image. This is where refracting telescopes keep their advantage. Their glass lenses can provide the highest levels of sharpness and contrast, letting astronomers observe fine details on planets and moons within our own solar system. Unfortunately, there is a hard physical limit to what is possible with glass lenses. The Yerkes Observatory in Williams Bay, Wisconsin, houses the biggest refracting telescope ever constructed. It was finished in 1897 and has a primary lens that is 40 inches, or 1 meter, in diameter. That single lens weighs 500 pounds, or 225 kilograms. The telescope is considered a masterpiece of late 19th century engineering. Nothing on this scale has been attempted since, and it likely never will be again. This helps explain why mirror-based reflecting telescopes ultimately became the standard. The largest telescope built in the 1800s was called the Leviathan of Parsonstown, 83 meters across. The tube itself was 56 feet long and was mounted between two stone walls that were 40 feet high. The telescope was moved using a system of chains, ropes, and pulleys, allowing operators to point it anywhere in the sky. With this enormous instrument, astronomers could clearly see the spiral shapes of other galaxies for the first time, like the Whirlpool Galaxy and the Crab Nebula. At the time, they didn't fully understand what they were seeing. The general belief was that these were large, interestingly shaped clouds of dust. This meant the clouds could be both unimaginably large and incredibly distant. They weren't made of dust, but were, in fact, vast collections of stars. This is where modern astronomy, as we know it, truly began. In the early 1900s, a group of astronomers in California began combining direct observation with the scientific method. You might recognize one of them, Edwin Hubble. This team started integrating huge telescopes with laboratory facilities, creating the modern observatory. The Mount Wilson Observatory, situated in the mountains north of Los Angeles, completed work in 1917 on one of the most significant telescopes in history, the 100-inch reflector. It would remain the world's largest telescope for the next 30 years. During that time, some of the most crucial discoveries in astronomy were made, many by Edwin Hubble himself. In 1923, Hubble aimed his telescope at a large gas cloud known as the Andromeda Nebula, and he noticed something fascinating. He identified a very special kind of star within the cloud, known as a Cepheid variable. These stars are unique because they pulse, growing brighter and dimmer in a regular, repeating cycle that takes only days or weeks. The star physically expands and contracts. By timing the speed of this pulse, astronomers can determine the star's true brightness. Essentially, the slower the pulse, the brighter the star. By measuring the pulse of this star, Hubble knew it had to be extraordinarily bright. But through his telescope, it appeared very faint. This could only mean one thing: the star was incredibly far away. Hubble concluded that Andromeda could not be a simple cloud. It was a gigantic system of stars, so distant that it had to be completely separate from our own star system. This was the first solid evidence for island universes, which we now call galaxies. Andromeda is the closest galaxy to our Milky Way, so it was the easiest to identify. Once Hubble perfected his method for finding these objects, he started discovering many more. Galaxies were everywhere, in every direction. The true, immense scale of the universe was beginning to be understood. But there was one more major discovery. Hubble also observed that all these galaxies were moving, and they were all moving away from us. This showed that the universe is not stationary and doesn't move as one single cluster. It must be expanding outward. If the universe is currently expanding, then at some point in the past, all these galaxies must have been much closer together. Hubble didn't invent the Big Bang theory. That was Georges Lemaitre. But Hubble's proof of the universe's expansion gave the Big Bang theory credibility and established it as the leading explanation for the origin of everything. From this point, telescope development continued in two main directions. The first was, of course, size. Bigger is always better. The 100-inch reflector was eventually replaced by a 200-inch model, and so on. But there was also a revolution in the scientific instruments that could be attached to these telescopes. We began to detect light beyond the range of human vision. New laboratory tools allowed for the observation of ultraviolet and infrared light, as well as more complex forms like radio waves and microwaves. The fundamental design of the reflecting telescope stayed the same, but the technology supporting these observations grew massively with the arrival of computers. Eventually, we began to hit the limits of what a telescope on Earth can achieve. So, we took the next logical step. We went to space. Let's discuss why launching a telescope into space is so beneficial. It's not about getting closer to the stars and planets. It's actually about getting farther away from Earth. Despite centuries of progress, a telescope is essentially just a tube that collects light. And as technology advanced, Earth itself began producing much more light, creating interference that makes it hard to see the fine details of the distant cosmos. To escape these limitations, NASA developed the first space-based telescope and named it after our old friend Hubble. The main advantage of a space telescope is the ability to continue the work of Hubble and his peers, to see deeper into the universe than could ever be possible from the ground. There are, however, pros and cons to a space-based observatory. One major drawback was that the Hubble telescope had to fit inside the Space Shuttle's cargo bay. While the bay was large for a satellite, it was quite small for a powerful telescope. 4 meters, smaller than the telescope the real Mr. Hubble used decades before. But what it lacked in size, the space telescope made up for with advanced technology. It used digital cameras capable of detecting light far beyond what our eyes can see. Here's a simple explanation. Light travels in waves, and these waves exist on a spectrum from very high frequency to very low frequency. The part we can see is just a small section in the middle. Above visible light is ultraviolet, and below it is infrared. Hubble can see the entire visible spectrum, all the ultraviolet light and some of the infrared spectrum, known as near-infrared. This capability is crucial because as light travels across the universe over billions of years, its waves get stretched out. What starts as high-frequency ultraviolet light from a star eventually becomes low-frequency infrared light. To observe the oldest light in the universe, to look back into the deep past, you need access to those infrared frequencies. This is very difficult to do from Earth's surface because of all the interference from heat and light. The Hubble Space Telescope achieved 2 incredibly important things. First, it produced stunning images of amazing places within the Milky Way and nearby galaxies. Second, and perhaps more importantly, it began investigating the very origins of the universe. Through its observations, we were finally able to determine the age of the universe, 8 billion years. Hubble also found evidence for dark energy and dark matter, the invisible forces thought to be driving the universe's expansion. It also discovered that nearly every major galaxy, including our own, has a supermassive black hole at its center. These discoveries laid the groundwork for much of what we believe about the cosmos. Yet, we knew we weren't getting the full picture. Hubble only touched the near-infrared spectrum. It couldn't see further because, from its orbit, there was still too much interference from the sun. What was needed was a telescope that didn't just orbit Earth, but one that could hide in Earth's shadow, where it could gather the oldest and most distant infrared light in existence. This need drove NASA to create the James Webb Space Telescope, an evolution of Hubble designed to overcome previous limitations. While the James Webb and Hubble telescopes look very different, the biggest change isn't just the design, but its operating location. While Hubble orbits Earth at an altitude a bit higher than the International Space Station, NASA placed the James Webb 1 million miles away, far beyond the Moon, at a spot called the L2 Lagrange point. This is a location where the gravitational pulls of Earth and the Moon essentially balance out. If you place an object at a Lagrange point, it won't be pulled into orbit around either body but will travel along with them through the solar system. It's essentially a parking spot in space. By parking the telescope at the L2 point, it remains permanently in Earth's shadow as our planet moves around the Sun. This alone blocks a huge amount of the Sun's infrared interference. But the James Webb also has a 7-layer sunshield to place it in even deeper darkness. On the shielded side, there's no need for a tube around the two mirrors because there is no light left to block. This allowed NASA to do something special with the main mirror. They designed it with folding hexagonal tiles, allowing the mirror to fit inside the relatively small cargo bay of a rocket during launch. 5 meters. This mirror's size rivals the largest telescopes on Earth, but it has the added advantage of operating in total darkness at all times. This is why NASA uses the James Webb primarily for infrared astronomy. This telescope is showing us the universe in a completely new way. It is getting a clear view of some of the oldest light in existence, taking us all the way back to the moments just after the Big Bang, if the Big Bang even occurred. The fascinating thing about the James Webb is that its vision is so unique we are only starting to interpret what it reveals. We aren't getting definitive answers yet, just more profound questions. And that is a good thing. That is how the process of discovery has always worked. The telescope is just a tool that shows us new possibilities. Then, human curiosity and the rigorous process of science take over from there. If you found this journey through the history of the telescope as fascinating as I hope you did, please show your support by liking this video, subscribing to the channel for more explorations of science and the cosmos, and sharing it with anyone else who might be curious about the universe.